Today we're going to discuss continuity, and continuity comes to us in section 1.4. There's three rules of continuity. If we think about continuity, it's a continuous. So what does it mean to be continuous? Well, if we start from the left side, or from negative infinity maybe, or we get any value, we're going to be able to draw this function, however funky and fun it is, we're going to be able to draw it without picking up our pen or pencil. And that would be a continuous function. So maybe one that would be non-continuous or discontinuous would be maybe something that we would come up, and then we'd have a jump, and then we'd go up like this. So we'd have a jump discontinuity in that one. Or maybe we come up, we hit a hole, and then we go on throughout. And then this, we would have a removable discontinuity, or point discontinuity. So, three rules of continuity. And we're going to look at this through the eyes of calculus. The first rule is that for every a, there exists an f of a. What does that mean? Well, that simply means that anywhere along our graph, for any a value, maybe a is here, then the value is going to exist. So we're going to be able to find a value at that point. So as I move a across my x-axis, I can always go up or down and touch this graph. I can always find a value for that graph. Number 2 says for every a, there exists the limit as x goes to a of f of x. What does that mean? Well, again, if I come up here to my graph, as I look at a, then the two branches are going to come together. So the limit from the negative side is going to equal the limit as x goes to a from the positive side. So as I go from the left side, is going to equal the limit to the right side. So we're going to be able to find the limit for that. And then number 3 says f of a equals the limit as x goes to a of f of x. And that tells us that when we found the value in number 1, it's going to also equal the value that we get in number 2. The thing with our rules for continuity, 1, these are universal. So anywhere you go in the country, world, you're going to know, if you talk about the rules of continuity, that 1, there's always an a, that the f of a exists. Number 2 is always going to be the limit is going to exist. And number 3, the value is always going to equal the limit. So when you talk about the second rule of continuity, everybody knows what that second rule of continuity is. So we can describe the continuity of a function by the rules that it passes or fails. Also, once we find that one of the rules fails, we can say it's discontinuous. We don't need to go on to rule 2 or 3 if rule number 1 fails. Likewise, if rule number 2 fails, we don't need to go on to rule number 3, because once 2 fails, we found discontinuity, we're done. So let's go ahead and look at a couple of examples. One, we have a rational function, and then we'll get into some piecewise functions where we normally look to see what we have for continuity. So in example 1, we have x minus 3 over x plus 2. So the question is, well, what are we looking for, and what value are we interested in for x minus 3 over x plus 2 with this function? If you remember, when we talk about a rational function, that denominator is very important to us, because we know that denominator cannot equal 0. So that's going to give us a hint on what a value it is when we talk about the continuity of this function. So we know that x plus 2 can't equal 0, so x cannot equal negative 2. So we know that this function is discontinuous at negative 2. Because remember, if we graph this, we have an asymptote, a vertical asymptote at x plus 2. So we know that this is discontinuous at x equals negative 2. Well, what rule fails for this function? If I were to take negative 2 and plug it into this function, for rule number 1, for every a there exists an f of a, so we know that if we took and found f of negative 2, we know that does not exist. So we know that rule 1 is going to fail. Then we can go on to part C there and ask us to state the intervals of continuity. So where is this function continuous? Well, we're going to be continuous on all intervals except when x equals -2. So we can say that it's continuous from -infinity to -2, exclusive, union, exclusive -2 to infinity. So we can plug in any value except for -2 and be able to get a function, a value, and a limit for this function. Hopefully you remember, if we have a rational function, we'll go back to the, if you remember the parent function, f of x equals 1 over x, looks something like this. It doesn't look like that, does it? Looks like this. So for every a value on the left side of 0, we know that it was continuous. And on the right side of 0, that's continuous. So again, we can play with that to get it to look like the x minus 3 over x plus 2. What we really wanted to talk about today is the piecewise function. And that's really where we're going to see our continuity come into play quite a bit. So here in example 2, we have f of x equals x plus 1 if x is greater than 1, and 2x minus 1 if x is less than 1. So the first thing we want to do is discuss, well, at what point is there something happening at? So we know from the right side of this, x plus 1 is a linear function. All linear functions are continuous. Likewise, 2x minus 1 is a linear function. So that's always going to be continuous. So we know the left and the right side of 1 is going to be a continuous function. Something's happening here at 1. We're breaking this function at 1, or it's changing looks. So we know our a value is 1. And we have a piecewise function. They're going to pretty much tell us our a value there. So we're going to test 1, and rule number 1 is what is the value when x equals 1 of this function. In this case, we're looking where does x equal 1? We either have a greater than or we have a less than. We don't have an equal to sign here. So f of 1 does not exist. So rule 1 is going to fail. So how do we put that into words? Well, we can say that this function is discontinuous at x equals 1 because rule 1 fails. We can also say that it's continuous on the intervals -infinity to 1, exclusive 1 to infinity. So we can either talk about the discontinuity or the continuity of this function. In example 3 here, we have x plus 1 if x is less than 1, 2 if x equals 1, and 3x minus 4 if x is greater than 1. Again, we're going to go through our 3 rules of continuity. The first rule, we're going to find f of our a value. Again, our a value is going to be given over here. We know that a is going to equal 1. So we're going to find f of 1. Where does x equal 1? It's going to be in this middle part, or this middle piece. So we know if we plug in 1, we get 2 out. So we go on, since we get a value, we go on to rule number 2, and that's going to be find the limit as x approaches 1. What has to happen for the limit to exist? That tells us that the 2 branches have to come together. So we're going to break this up into 2 limits. We're going to look at the limit as x goes to 1 from the negative side, and the limit as x goes to 1 from the positive side. From the negative side, we're the less than side, so if I plug in 1, I get 2. If I plug in 1 from the positive side, I get 3 minus 4, which gives us -1. These 2 limits are not the same, so we know the 2 branches don't come together. So we know the overall limit as x goes to 1 does not exist. So we can again discuss the continuity here. We can say that this is discontinuous at x equals 1 because rule 2 fails now, since our limit doesn't exist. Or we can say it's continuous on, again, we have a linear function and a linear function from the left side and the right side. All linear functions by definition are continuous. So we're continuous from negative infinity to 1, union 1 to infinity. So again, it depends on how the question's asked. We can discuss the discontinuity or the continuity of the function. We have just a couple more examples, and hopefully we'll see an example of each of the things that could happen. In example 4, x minus 1 if x is less than 3, 4 if x is equal to 3, and x greater than minus 7 if x is greater than 3. So rule 1, again, our a value is 3, so we're testing f of 3. So where does x equal 3? Again, in that middle part, we know that that's going to give us 4. So then we go on to rule number 2, which is the limit as x approaches 3. Again, we're going to break this up from the negative side and the positive side of 3. Well, from the negative side, we're at the less than side, so I plug in 3, I get 2. From the positive side, or the greater than side, if I plug in 3, I get 2. So then, since these two values are the same, I know that my overall limit exists. So now when my value exists, my limit exists. So number 3 says, rule number 3 says, well, does the value equal the limit? Does 4 equal 2? And of course, no, it's not. So we know that this is discontinuous. At x equals 3, because rule 3 fails. We can also say that it is continuous on the intervals. Well, we know it's continuous on the left side because it's a linear function, and on the right side it's a quadratic function. And again, by definition, we know a linear function is continuous and a quadratic is continuous. So it's continuous on negative infinity to 3, exclusive union 3 to infinity. And in our last example, number 5 here, we're going to go ahead and look at the value. Again, our a value is negative 2. So we're going to find f of negative 2. Again, that gives our middle statement there, which is negative 2. Rule number 2, we're looking at the limit as x approaches negative 2. We're going to get from the positive side and the negative side. Gets kind of redundant writing this out, but we definitely want to show all of this work so that we can prove that it's either discontinuous or continuous. This would be our justification of our work. So I plug in negative 2 from the negative side, and for my x I get a negative 2. From the positive side or the right side, or the greater than side, if I plug in negative 2, I get negative 2 out as well. So the overall limit exists, which is negative 2. So I go on to rule number 3, and that says, does negative 2, our answer from 1, equal the value that we get from 2? So does negative 2 equal negative 2? And of course, yes, it does. So that we say then it is continuous for all x values. You can also put from negative infinity to infinity, since we know from the left side it's a linear and the right side it's a linear function as well. And that concludes our discussion on a continuous function. Happy continuity!